Today we have Eckhard Meinrenken, who will tell us about the symplectic geometry of Teichmueller spaces for surfaces of ideal boundary.
Yeah, thanks a lot. So a very long title. So this is joint work with Anton Alexeyev, and this is the talk's based on a paper with pretty much the same title, which is already published in Communications in Mathematical Physics, easily available because it's open access. Right, I've spoken about this material before, but I think nobody in the audience has been at those earlier talks, as far as I can remember. So let's see how it goes. I'll start out with motivation. So we were motivated to do this project basically from two perspectives. One was more mathematical and one was more physics. So the physics motivation is what's called Jacques-Teitelbaum gravity. And honestly, I do not know what that is. Don't worry. So Anton had suggested that we should look at those recent papers on JT gravity because they include some very nice pictures. So the papers I mentioned, I'm talking about especially Sarge, Schenker, Stanford. It's kind of Schenker, Stanford, it's a famous one. And I think, is it 80, 90, no, 2019. Mm-hmm. And then there's Stanford written, and so mostly with Stanford as a co-author. So what they're looking at is some Riemann surfaces with wiggly boundary. That's what they call it. So they consider Riemann surfaces, but non-compact Riemann surfaces. So Riemann surfaces that can develop funnel ends. By Riemann surface, I mean with a hyperbolic metric. So these pictures, something like this. Funnel ends, and then I could have some genus. So these are infinite Riemann surfaces, if you want, and the volume is infinite. And then they consider certain partition functions which involve integrals over those Riemann surfaces. But they have a problem because those Riemann surfaces are infinite. The integrals don't converge as they stand. So they come up with a very simple solution. They just cut off the boundary. And those are these wiggly boundaries they introduce. So they cut off the Riemann surface with some curves, call it the wiggly boundary. And then they have some integrals over the surface that is left over. But then, of course, it depends on this choice of wiggly boundary. And then they say, it's no problem. We just do a path integral over all the wiggly boundaries. So at that stage, like mathematically, it sounds a bit suspicious, maybe. But then you look further into the paper and they get all kinds of interesting things out of it. I mean, there's Verzeau algebra and Schwarzian derivative, of course, makes its appearance. And there's some Heckman theory, Mirzakhani recursion formulas. And there are hundreds of pages and lots of interesting mathematics apparently going on. So there seems to be something to it. So we're trying to kind of understand these pictures, and just looking at the pictures without looking at the formulas, which we didn't really understand, we came up with the idea that what these pictures suggest are some kind of infinite dimensional Teichmueller spaces. Well, thinking these should be Teichmueller spaces where you look at hyperbolic metrics on a surface with boundary. I mean, so we think of the surface really as some finite surface with boundary. But the metric only exists on the interior of the surface, so to speak, with a certain boundary behavior. And then you divide out by diffeomorphisms, which fix the boundary. So it's an infinite dimensional space still. on which one then still has the diffeomorphisms of the boundary, so there's some room for Virasoro in the picture. Right, and we want to make sense of such a space, of this infinite dimensional space, as some Hamiltonian Virasoro space. So the group that's acting roughly should be the diffeomorphisms of the boundary. So it turns out, strictly speaking, it's the universal cover of that what's acting, and should be a Virasoro moment map in the picture. And if I say moment map, there should also be a symplectic structure in the picture on this space. Right, and the mathematics motivation for us was that we had earlier developed some theory of Hamiltonian loop group spaces. And our main point was that these Hamiltonian loop group spaces, even though they're infinite dimensional, they have some sort of finite dimensional counterpart. So you can treat them in a completely finite dimensional way. And we had come up with something similar for Virasoro spaces. And while we were looking for examples, and this should be one of our examples.
So if there's a disk and just simple case, then what is there some kind of clear identification what will it be?
Yeah.
Then is it just a pure Virasoro orbit or?
The space would actually be a Virasoro orbit. That's correct. Yeah.
So when it's a disk and
when it's a disk, then it's a certain Virasoro orbit. What you get out of it. Right. So let's be more specific about what I mean by hyperbolic structures. Right. Hamiltonian reduction of this space with respect to yes, right. So as I'm saying, so we have some finite dimensional version of this space where the space with an action is already finite dimensional, and then in particular the symplectic quotients are finite dimensional. The only issue is that the group that's acting is not compact. It would be PSL2R, and so the quotients might be ill-behaved, but finite dimensional. Right. So let me be specific what I mean by hyperbolic structures. Well, the model that we're using throughout is the Poincare disk, which I denote by a D. So D is the Poincare disk. Maybe I just draw the picture. So the geodesics are circles which are orthogonal to the boundary. Not really orthogonal, but okay. It's supposed to be orthogonal to the boundary. Right, with a Poincare metric. What is it? In complex coordinates. Right, so this is the model. I could also work with the upper half plane, but Poincare disk works better for my purposes because I kind of want to include the boundary. And if I do the upper half plane, then I have to point at infinity. I don't want it to be at infinity. I want everything to be visible. Everything is in the picture. So Poincare disk is somewhat better. So the group of isometries of this Poincare disk would be the group PSU 1, 1. So if one works with the upper half plane, then the group that one would get would be PSL2R, which maybe is a bit more familiar. We don't need the specific group really. It's just that there's this three-dimensional Lie group in the picture, which acts by orientation preserving isometries. That's, so to speak, our symmetry group. Now the definition of hyperbolic structure. So let's sigma be surface for first class without boundary. Later I include the boundary. Then I say a hyperbolic structure on this surface is given by an atlas with charts taking values in the Poincare disk. So that's my model space, and transition functions between two such charts given by elements of this G. So I'm gluing these charts together with projective transformations.
This is G isometry.
Yeah, that's from now on, just use the notation G. Yeah, that's right. So that's the definition. Right, and then the usual Teichmueller space, one would define, one way of doing it is, say it's a set of hyperbolic structures up to identity component of diffeomorphisms. So up to isotopy. All right, so before I get to the case with boundary, let's first summarize a few things that are known about the usual Teichmueller space. Some basics. So the first thing to say is maybe that this space of hyperbolic structures. Sorry, I didn't introduce this formally. This Hüb sigma means the set of hyperbolic structures. You can also view as a set of hyperbolic metrics. On sigma, right? So hyperbolic metric meaning Gauss curvature equals -1. Because using these charts, you can just transfer the metric from the Poincare disk over to the surface, and then they glue together. So the way I've defined it doesn't really require the metric, but that's one way of looking at it. Right. About the structure of this space, well, it turns out it actually has a very simple structure. It is a manifold, and it's actually a very simple manifold. It's R plus times R to the power 3G minus 3. Where, okay, little g means all kinds of things. Right now, it means the genus. And this is by Fenchel-Nielsen coordinates. So what one does is, okay, a little bit of hyperbolic basics. If you have a pair of pans, so as a surface now with boundary, and we're looking at hyperbolic metrics with the property that the boundaries are geodesics. So it's a basic fact that once you specify the lengths of those boundary geodesics, there exists a unique hyperbolic metric up to diffeomorphisms for those three lengths. So this is basically your model piece. And now we can get more complicated surfaces by gluing together those pairs of pans. So make another pair of pans here. So these L's are the length parameters, they're positive. These are R plus. Now the other parameter, the way it comes in is on the pair of pans, one also has seams. So orthogonal to each boundary component, there's a unique geodesic, which starts out orthogonal to the boundary component and ends up at the other boundary component orthogonally. So that's called a seam of this pair of pans. And there are three such seams. Now, when you glue together those pairs of pans, you don't have to align those seams. You can kind of rotate. So the neighboring surface might have the seams like this. with a little twist. And because we're only looking up to diffeomorphisms, only up to isotopy, you can even twist like a jumpsuit of a baby, right? So it could kind of wind around a few times before you glue them together. So that's those twist parameters. To actually make them well defined on the surface, one has to put in a little more thought, but that's the basic idea. So these are the length parameters and the twist parameters. So let's call them Li, and Ti. So on the general closed surface, that's exactly the parameters one needs, and then it's just a space like that. So very, very simple.
This parameter is up to 2 pi?
No, that's the thing. So if you look at this, if you look at hyperbolic structures up to diffeomorphisms, up to all diffeomorphisms, then it would be modulo 2 pi. But we're looking at them up to isotopy. And so therefore, you can still see if a geodesic maybe twists, like winds around a couple of times. Right, so these are these differential-Nielsen coordinates. The third fact is that there exists a symplectic structure on this Teichmueller space. So there's a symplectic structure. Because historically, the symplectic structure was kind of last. I mean, when people developed Teichmueller theory, there was first this series of quasi-conformal mappings, and then the Riemannian structure was important, the complex structure was important, and then there was a conjecture that it was scalar, and then it was proof that it was scalar. So the kind of symplectic structure was kind of discovered at the very end in some sense. Basically because back then symplectic geometry wasn't so popular yet, I imagine. So maybe 1960s or so, the symplectic structure was realized. But because it came from such a strange angle, it was a kind of difficult thing initially, the symplectic structure. And then it was discovered that in terms of these differential-Nielsen coordinates, it's actually just Dabu. So never mind the factor 1/2. These differential-Nielsen coordinates are just Dabu coordinates for the symplectic structure. So this was proved by Wolpert in 1983, yeah. So quite late in the game. So the structure was known in the 60s, but then took this long to see that it's simply that in differential-Nielsen coordinates. And if you take this as an initial definition, it's certainly not so obvious also that it does not depend on the choice of Pence decomposition, right? There are lots of choices involved in the Pence decomposition. And you always get the same symplectic structure. Right, then there's another way of looking at the symplectic structure as follows. Okay, there's a canonical map. Teichmueller space to, okay, this is my notation, moduli space of flat G bundles. Flat G bundle, principal G bundles. I mean, where does this map come from? It actually comes from a map. Okay. Teichmueller space is a quotient of hyperbolic structures. And actually, every hyperbolic structure determines a flat principal G bundle. If you look back at how we defined it, we said it's given by these charts with Atlas, transition function is just elements of G. So in some sense, the transition function is just constants. So these elements of G as transition elements, they define a principal G bundle, which is flat. So that's where the bundle comes from. Right, so that G bundle. And then you can see if you change this by some isotropy, then the flat G bundle doesn't actually change, only changes up to isomorphism. So that's this map. Now, in our case, the group G is not simply connected. I mean, G is isomorphic to PSL2R. It's not simply connected. And this means that this moduli space, okay, no, sorry. Since the group is not simply connected, there are non-trivial G bundles over the surface. So the isomorphism classes are principal G bundles. If I don't talk about the connection yet, is classified by the fundamental group, right? That's how it goes in general for any connected Lie group, which in our case is, so the group is PSL2R, then the fundamental group is the integers. And the principal G bundle that appears here is not just anything, it's the, so what's the corresponding integer? The integer turns out to be the Euler characteristic of the surface. So here get, okay, so I'm calling this kind of class of the bundle, the Euler number of the bundle. So in our case, the Euler class of the bundle is the Euler characteristic of the surface. So you don't get the entire moduli space, you only get the part which corresponds to that topological type. And now it's actually an interesting story also. Yeah, there's a question, which principal G bundles actually do admit a flat connection? There's this famous Milnor-Wood inequality, which says principal G bundle for this group PSL2R emits a flat connection if and only if that integer is between plus or minus the Euler characteristic. And so the extreme one, that's exactly the one for Teichmueller space. Okay, and okay, so I'm saying all this because there's a theorem due to Goldman and Hitchin, which says that this map is actually an embedding, and the image is just simply a connected component. Namely, the connected component corresponding to that Euler characteristic. It's exactly that. So that was proved, when was it, 87? Yeah, 87, 88. Yeah, 1987. Right, so you can view Teichmueller space as a connected component of the moduli space of flat G bundles. And on the moduli space of flat G bundles, one has another famous symplectic structure, which is the Atiyah-Bott symplectic structure. like moduli space of flat connections on the principal bundle. And yeah, the symplectic structure is, and they proved that also, symplectic structure is just this Tia-bot symplectic structure. So that's another construction, if you want, of the symplectic structure on Teichmueller space. It's literally the moduli space of flat G bundles. So meaning, okay, so you can actually rephrase it and say we now fix some principal G bundle of that topological type, and then we look at flat connections on that G bundle's application transformations. It's literally that on the nose. So there are no caveats. Interestingly, that moduli space is automatically smooth. I mean, as we know, right, Teichmueller space is smooth. So that's also part of the theory that they're proving. So the bundles emit flat connections if and only if it's between plus or minus the Euler characteristic. The one to the integer corresponding to integer 0, that is singular, but all the other components are smooth.
Is that map symplectic?
Is it what map? So, so what I'm saying is that this map is not an isomorphism because there are some other topological types. But I mean, this is just a disjoint union of components to correspond to topological types, and it's an isomorphism onto one of those components.
Yeah, I guess like, does it preserve the symplectic structure?
Yes. So the standard symplectic structure on Teichmueller space is just the Tia-bot structure here. So if you want, it's another way of defining the Teichmueller symplectic structure. Okay, so that's all I want to say for now about the case without boundary. Now I should specify what we mean by a hyperbolic structure on a surface with boundary. So that's why I want to keep this up. So now we want to allow for the surface to have a boundary. Then how define a hyperbolic structure? Well, it's actually quite simple. I simply work, instead of the Poincare disk, I work with the closure of the Poincare disk. Otherwise, it's just exactly the same. So when I say charts here, I should be specific about what I mean by smooth map. So it should really take boundary to boundary, and the kind of boundary defining functions should be compatible in that sense. So the charts kind of model the behavior near the boundary of the Poincare disk. That's the idea. So we have a hyperbolic structure on the surface of the boundary, and near the boundary, it just looks like the boundary of the Poincare disk. And otherwise, it's exactly the same definition. Very simple. Right, and now, as I did before, now we define Teichmueller space a bit differently. So now we take the set of hyperbolic structures, but then we only divide up by diffeomorphisms which fix the boundary pointwise. This is my notation for that. So this is now our infinite dimensional Teichmueller space. Okay. I don't want to give such a long list of basic facts now, but few basic facts. I can again say this in terms of metrics also. So this set of hyperbolic structures in this sense, now for the surface with boundary, is what we call hyperbolic zero metrics. What do we mean by that? So I mean, I said we have the hyperbolic metric only on the interior, but I still have to specify a little bit what happens near the boundary. And well, zero metric means, it's not the best definition, but one definition would be that if you look at the, let's say we introduce coordinates near the boundary x and y, then this means the metric goes like 1 over y squared. That's how it blows up. So that's exactly the kind of way in which the metric on the Poincare disk blows up. And so one can show that this is really equivalent. I mean, there's another way of defining zero metrics. There's this so-called zero tangent bundle, which is a vector bundle whose sections are the vector fields vanishing along the boundary, and then it's literally a metric on that zero tangent bundle. That's the better way, but we don't need that. That's just how it was called. I mean, it's similar to this B metric that Melrose invented for manifolds with boundary, for analysis of manifolds with boundary, and then they had another version, which they then called zero metric. I guess zero because it vanishes. Right. Okay, so in terms of examples, well, the Poincare disk itself, of course, is an example. It's not too interesting. Another basic example is what we call the double trumpet. So we're kind of adopting the physicist terminology. In math, these things are called more funnels or flares sometimes also. But the physicists call them trumpet, and that sounds more funny. So picture is like this. So there's a hyperbolic metric on this cylinder. In the middle, there's a geodesic of some length L. And the metric is given by some explicit formula. So if I say this coordinate is u going from -infinity to infinity, and this coordinate is x, then hyperbolic cosine squared L squared dx squared times du squared. So that's a hyperbolic zero metric. So if you introduce, as I said, u goes between -infinity and infinity, but if you introduce a boundary defining function, you're going to find it blows up exactly like 1 over y squared. And then for higher genus, well, basically, with the picture before, you can kind of glue some easy pieces to make higher genus things. Basically, what you do is you glue half of such trumpets, draw it like this. I should make it go more out. So you draw these half trumpets. No, they're trumpets. These double trumpets, so those are trumpets. You glue trumpets, and then in the interior you have, again, a pans decomposition with lots of pairs of pans. Right. Yeah, and actually, one has again potentially needs a description of the space. So the Teichmueller space is going to be so there's some part which comes from this interior stuff. This is 3g plus r minus 3. So R is the number of boundary components. There's just something coming. R is the number of boundary components. And for this 3g plus r minus 3 is all these like inner circles that we use to cut. in the Payne's decomposition. So for each of these circles, there's a length parameter and a twist parameter. And then there's some contribution of the trumpets, and that's one length parameter, right? Kind of this length, which I have, and then we can kind of twist the end of the trumpet. Which basically just gives the diffeomorphism of the circle, but actually universal cover because we can twist all the way we want. And this to the power R, right? So one such thing for each trumpet. So this is literally the space that we want to deal with and want to define a symplectic structure on it and moment map. Okay, any questions?
These are only the cases where you have some bunch of trumpets, or are there any other?
Yeah, those basically all the examples. Yeah, yeah. This is a complete list of examples if you want. Mm-hmm. I mean, you could introduce some other versions of examples where you have some surface with some geodesic boundaries of specified length or so. It's like specifying holonomy around some boundary components. So those kind of extra examples you could introduce also. But literally for the space I've introduced here, those are really all the examples. Mm-hmm. All the examples, I mean, even here, of course, you can take the Poincare disk, but then you can act on the Poincare disk by some diffeomorphism to make a new metric. Right, and so that's why the Teichmueller space is not just a point; it's going to be much larger, and actually ends up being a covariant orbit for the diffeomorphism group indeed. And likewise here, so you can take this kind of basic metric and then you can start twisting. Okay, so the question now is how to define the symplectic structure and how to define the moment map. And I want to start with the moment map because that's actually easier in a way.
Here, the boundary at infinity is part of the data.
Yeah.
The hyperbolic, like just regularly, just a infinite volume hyperbolic surface. And one define the boundary at infinity. It should be like a bunch of circles.
I'm not sure. I mean, boundary at infinity. So in some sense, it is a finite boundary, right? We're looking at the surface with boundary, and the boundary is included, and then we are specifying how the metric kind of degenerates along the boundary.
Yeah.
I mean, from the perspective of the metric, it's at infinity, but right. So let's start with a discussion of momentum map. And to define it, I think I still have these things up here. Yeah, I want to go back to this again and define in a similar way, like how define the hyperbolic structure, the notion of projective structure. Okay, so okay, we can keep this, but let's say we have at C a compact oriented one manifold, or just a bunch of circles and lines if you want, but no preferred parameterization. I mean, I can define, of course, projective structure in higher dimensional things, but I only need it in the one-dimensional case. Then let's say a projective structure. projective structure on this one-dimensional manifold is an atlas with charts, and now the charts take values in the boundary of the Poincare disk, which I can think of as RP1. See, I don't take this boundary.
So it's only circle.
Yeah, no, or like lines. Oh, compact, yeah. Okay, then it's just circles. Yeah, here it just need for circles, yeah. Yeah, I could, I could,
Lines. I was wondering.
yeah, I could admit they compact. Yeah, it's actually not important. Right, and otherwise it's the same thing. So, I mean, usually you would say projective structure is given by atlas with chart values in RP1, but for me it's better to think of RP1 as the boundary of the Poincare disk. And the transition maps again are defined by elements of G. So if you think of RP1, then G would be PSL2R again, with the usual action on RP1. Right, so in this way we can define projective structure. And right, having defined projective structure in this way, you see immediately that note a hyperbolic structure on a surface, where the surface might have boundary, induces a projective structure on the boundary. Obviously, right? Because you just take the charts which you have for the hyperbolic structure on the surface and just restrict them to the boundary. Right? Or charts, in the case with the boundary, take values in the closed Poincare disk and take the boundary of the surface to the boundary of the Poincare disk. So kind of obvious. Right. And yeah, this is in some sense going to be our moment map. So we have the space. We have Teichmueller space. Okay, Teichmueller space, the portion of the set of hyperbolic structures. As I said, there's the map which goes to projective structures on the boundary. Would be my notation for projective structures on the boundary. But if you change the hyperbolic structure by some diffeomorphism which fixes the boundary, what happens at the boundary doesn't change. So it descends, well, ascends to Teichmueller space. So that's this map. And this map is going to be our moment map for a symplectic structure eventually. Okay, but you can see that on these things, there's an action of diffeomorphisms. There's an equivalent map, and this is going to be our moment map. Now, this might seem a little bit strange yet, because projective structure seems kind of a weird thing, right? I mean, we would prefer if a moment map takes values in some decent vector space, not in some sort of set. We don't have much feeling yet for how does this set of projective structures actually look like. But it actually is a very simple thing. And we can identify it also with what's called the space of Hill operators. So projective structures has the advantage of being more easily definable, but the Hill operators, which I explained in a moment, are more obviously an affine space. So not quite a vector space, but it's an affine space. So almost as good as a vector space. And then it makes sense to talk about moment map. Right, so let me talk about Hill operators for a sec. No, I was first going to give a description of the moment map and then talk about the symplectic structure. Because in some sense, symplectic structure is more complicated than the moment map, unfortunately. Right, so what's the Hill operator? If I want to do things coordinate free, then it looks a little bit means takes some time to get used to maybe. But it has the big advantage of being coordinate free. So again, we look at the C, not necessarily compact and oriented one-dimensional manifold, not necessarily connected. On this space, we can look at the space of R densities. Okay, what is an R density? Well, here's just a one-dimensional manifold. It's kind of easy to say what an R density is. It's just a map U from the tangent space to R with the property that if you scale it, goes with a factor like this. That's an R density. So the R densities are sections of certain line bundle over the curve. And now we can say definition. A Hill operator is a second order self-adjoint differential operator. L, which goes from, and this is now this kind of shocking part, goes from -1/2 densities to 3/2 densities with a principal symbol meaning leading behavior equal to 1. Okay, so this seems very confusing. Of course, if one sees it for the first time, but it's actually not so bad. So first of all, when I say self-adjoint has to make sense. If you take so what you notice is these are -1/2 densities and 3/2 densities. If you multiply them together, you get a 1 density, so you get a density, and densities you can integrate. Okay, maybe then I want C to be compact. Let's say C compact. Right, so in some sense, these spaces are dual to each other. So that already dictates a little bit which exponents one has to take here. And then is the question about principal symbol of an operator. So usually it takes values and homomorphisms from one vector bundle to the other vector bundle, tensor symmetric power something, right? So if you figure this out, in what case is that a scalar? It's precisely when you put these numbers there. And then it makes sense that that scalar is equal to 1. In coordinates, it's actually very simple. So in coordinates, say if C is connected and you identify C as 1, then a Hill operator is simply Schrödinger operator. That's how it looks like. However, so what the advantage of this description, the coordinate-free description, is that you see the diffeomorphisms of C naturally act on it. Right? There's some action of diffeomorphisms because the definition is coordinate-free. Diffeomorphisms act on the space of Hill operators. And then one can calculate and figure out what does it mean in coordinates. And yeah, it's actually interesting. So in coordinates, so the action of a diffeomorphism F on a Hill operator, let's put it like this. Let's see, how do I want to say this? Yeah, it's actually easier to say it the action of the inverse of diffeomorphism. So this would be again the Hill operator. So it's of this form. So it somehow acts on these T, the so-called Hill potential. And that formula is given by okay, so if this was just a function, then it would act like this, right? But it's actually not really a function. And because of that, there's a factor here, first of all, f prime squared, which would say that it more acts like a 2 density, a quadratic differential. And on top of it, there's some term here, plus 1/2 1 prime over a prime squared, the famous or infamous Schwarzian derivative. So, I mean, you could say, I might as well define everything in terms of coordinates directly, but then you end up, you have to have this formula. And it seems a bit unmotivated to do it like that, right? Right, so that's about Hill operators. Okay, now I was claiming that Hill operators are actually isomorphic to projective structures, and where does that come from? Well, it comes basically from ODE theory. So ODE theory tells us that you can, it's a second order ordinary differential operator, so you can look at fundamental systems of solutions. Let's say locally, because it's on a circle. So if you go around, then there's going to be some monotony. But let's say we just look locally for starters. So local fundamental system of solutions. U1, U2. So these are both these terrible -1/2 densities. So the local fundamental system of solution is going to be unique up to some constant rotation. And then I get so unique up to R G to R. Okay, maybe I'm lying a little bit, but okay, so the point is you have this fundamental system of solutions. And okay, they take values in -1/2 densities, but if you look at the ratio, that's well defined as a function taking values in RP1. Because again, by ODE theory, these two solutions, they never vanish at the same point. So as a map to RP1, it's well defined. And so you get a projective chart. And if you change your fundamental system of solutions, then changes by SL2R transformation. So there is a map from Hill operators to projective structures. And that map turns out to be a bijection. Okay, and so this in some sense now better if you want to have a moment map target, because the space of Hill operators, you can see easily that's an affine space. It's an affine space over, you can basically see it from here. You can add a function to this T. Not really a function, it's a quadratic, it's a 2 density you can add to a Hill operator always, also known as quadratic differential. So space of Hill operators is an affine space over the space of quadratic differentials. So pretty much like a vector space. Right, so that's better as a moment map, but then I'm saying it's supposed to act as a moment map for this group somehow. So still have some explaining to do. And okay, so there we go to Virasoro.
Take a break around 3. Coffee. Here's for 5 or 10 minutes.
Oh, yeah, we can.
Remember,
Yeah, maybe it's a good time. Okay.
come back. 5
Mhm.
minutes.
Yeah, so next thing is I'm going to explain that this is also a dual of the Lie algebra of Virasoro, basically. Class is dismissed. Okay, so I was going to explain what this has to do with Virasoro. Okay, so Virasoro Lie algebra. As you probably know, it's a central extension of the Lie algebra vector fields. So I'm going to do Virasoro Lie algebra again, coordinate free. So again, my C is in the picture. Vector fields on C. Right, and how to describe it? Well, central extensions like this. Okay, we also have the group acting on everything, right? Diffeomorphisms of C is the kind of group corresponding to vector fields, but because central extension, it will act on the central extension. And one way of kind of describing a central extension is always to go to the dual. So if you know kind of the coadjuvant action, then you know the central extension. So it can be described in terms of, let's say, the level 1 coadjuvant action. Right, if you dualize this exact sequence, so go Vir star, then it comes with a map to R. And so there's some level set, I do not like this. So this is the part of the dual which maps to 1. And all these hyperplanes, they are invariant under the action, again, because of central extension. And if you know this action, then you know what the central extension is. Right. And now what's the dual of the Lie algebra of Virasoro? Well, it's again identified. So this is some affine space, and we take it to be the space of Hill operators. And this is correct because this makes sense. Because the Hill operators are an affine space over quadratic differentials, as we said. And the quadratic differentials, they pair with vector fields. Right. Also, you could say basically it's like the dual of the vector fields, except it's, I mean, of course, like a smooth dual. There's a pairing between quadratic differentials and vector fields. So to say this again, so the space of Hill operators is an affine space, and its space of translations is identified with the dual of the vector space, of the space of vector fields. Right, and because of that, this affine action which we have in the space of Hill operators, which in coordinates with the Schwarzian derivative and so on, gives rise to a central extension, and that's the Virasoro algebra. So this is the coordinate-free description of the Virasoro algebra. Of course, one can again also describe it with in coordinates with a cocycle, and in some sense it's easier. But then again, a little bit unmotivated also. Right, so in some sense, it's then another way to look at it. It's also the dual of the Lie algebra of Virasoro. And now it sort of makes sense, I believe, right? So the diffeomorphisms of the boundary, they act on this. And this is a good target of the moment map. So when we came up with this space as a Hamiltonian Virasoro space, we literally thought the other direction. We kind of eventually, after reading relevant sections of Boris's book, we understood this part, that projective structures are same as Hill operators and relate to Virasoro. And so then we were looking for some space where the mode map takes values in projective structures, right? And that's how we came up with this.
In principle, you have as many central extensions as the number of connected components. But here you have the sum of all cocycles, right? So it's just kind of one cocycle for all connected components together.
Yeah, but we don't really think in terms of cocycles, right? We're just working with this affine space.
But in principle, you have kind of Hills operator on each connected component. So you keep the same coefficient 1.
Yeah, that's right. It's always the same coefficient 1. Yeah, throughout the story, there's always the coefficient 1. Okay. Right. So now, I mean, of course, this I'm always doing the kind of abstract coordinate-free description, but then you also want to work out what it means in coordinates, because then you tend to get nice formulas. And okay, so what is this in coordinates? So by in coordinates, I mean the following. I mean the following. So we have some element of our Teichmueller space, this hyperbolic zero metric. So we have some equivalence class of some zero metric there, huh? Just with this blows up like 1 over y squared near the boundary. So again, we introduce these local coordinates x and y. So it goes like 1 over y squared. And we want to map it to some Hill operator in coordinates. So question is, given this g in coordinates x and y, what's the formula for this t? Well, it's basically just a matter of calculation, right? Everything is explicit, just calculate. And what the calculation eventually gives is the following. Okay, so first of all, I mean, it uses the following ingredients. So this g, as I said, blows up like 1 over y squared. That's how the metric blows up. Then if you look at the corresponding volume form, it also blows up like 1 over y squared. So it goes like something over y squared, dx wedge dy, where plus higher order terms, where this coefficient here is some function of x. That's one ingredient. So this a of x. Another ingredient is, if one looks at, how to say this, maybe I draw this part of the picture like in the upper half plane. So this is x and this is y, it's upper half plane. It's well known that if you look at the hyperbolic metric on the upper half plane, you look at these lines, y equals constant. I mean, they're not geodesics, but instead they have geodesic curvature equal to 1. So we are not dealing with the standard hyperbolic metric in general. So it's not going to be one exactly, but we can look again at, okay, let's call it geodesic curvature. So this geodesic curvature of the curve where for some constant y, these kind of horizontal lines as a function of x. So it starts out with 1, but then there are correction terms, and the next correction term one finds is of order y squared. So that's the next ingredient. I get this right, yeah. So there are these two ingredients, these two functions. One comes from the volume form, the other one comes from geodesic curvature of these level sets. So in some sense, we're looking at kind of lines parallel in coordinates to the boundary and look at the geodesic curvature.
They're dependent. So
They're independent, yeah. Independent. A and C, they're independent, yeah. And then the formula for this T of x is given by the first term looks like Schwarzian derivative for good reason. Plus a squared over 2 times c. So there's an explicit formula of what this T is. But as I said, it looks nice, but it's just a matter of calculation, really. I just want to say everything's really very explicit. We can work out all the formulas. Right. So that's all I want to say about the momentum map. So we have our space, we have the action, we have the momentum map, and now we still need the symplectic structure. Yeah, symplectic structure end up being the hardest part for us. What's the hardest part? I mean, the idea was that it should be somewhere like some Atiyah bot construction, but it took us like forever to get it right. If we got it right, I mean, it works. I'm not sure if it's optimal yet. Right, okay, maybe this time I'll give you the formula first. Well, I should say in French-Nielsen coordinates. So if you recall, we said that this our infinite dimensional Teichmueller space is of the form, so length and twist parameters to the power 3g plus r minus 3, or these inner gluing circles, and then there's some kind of the length of this boundary of the boundary trumpets. And then for each trumpet, there's universal cover of diffeomorphisms, because you kind of twist the trumpet at the end. Okay, so in these coordinates, so here let's say we use the coordinates Li and Ti, length and twist. Here the length parameters I denote Mj. And then there's some diffeomorphisms, Fj.
The coordinates corresponding to the R in the component, R in the exponents.
Sorry, what?
Right.
This? Oh, sorry, G is the genus, and R is the number of boundary components.
The lengths of the trumpet.
No, these are not coordinates. Sorry, no. So we do our Pans decomposition. Right, so these inner circles, here we have length and twist parameters. And then there's some ends where the trumpet's attached. the trumpets, I call them MJ, these things. And then there's some diffeomorphism here, which kind of twists the end. Those are our parameters. So in those parameters, I can just write down what the symplectic structure is. So there's, again, the kind of ballpark part, DLI wedge DTI. And then the trumpet contribution can be written like this, integral over S1, the square of these lengths, Fj prime dfj plus dfj prime prime over fj prime. So integrated over the circle. Okay, one has to think a bit about what all these things actually are supposed to mean. So these f's, they're somehow thought of as functions on the space. And then when I write d of f, then it's a one form on the space. So it's this exterior differential is basically exterior differential on this infinite dimensional space. Whereas when I take a derivative, this is just a derivative if I think of it as a function from R to R, just the usual derivative. And the derivative itself is a function on that space. Right, and then I can take the second derivative, it's also a function on that space, and then take the exterior differential, then it becomes a one form. So this whole integral here is going to be a one form on my infinite dimensional space, and then I take d of it, it's going to be a two form on this space.
But if trumpet is attached to the pens, then MJ, does it correspond to Li on the other side, or?
No, they're independent. Yeah. So that's what I was saying. So I mean that's from the theory of these hyperbolic metrics on pairs of pans. So you can choose arbitrary lengths for those three boundary components, and there's a unique hyperbolic metric on it, realizing those three lengths. So those three lengths are just completely independent.
So it corresponds to the fact that we just can cut it in some sense anywhere distracted, and it will be corresponding.
Well, it is a geodesic, so it's not quite any for the metric. It's a geodesic.
But we can kind of provide this any length here by essentially just.
Okay, so that's a formula, but of course, I mean it's a formula, but it's totally unmotivated, and certainly hard to check directly that it does the job. Namely, that when you check the contractions with the generating vector fields for the diffeomorphisms, that you end up with our Virasoro map, right? So that's not how we want to go. We want to have some, as usual, coordinate-free description of this. And
But how did you come up with this formula?
well, at the end by calculation, after we had our general our abstract recipe. I mean, it doesn't quite come from nowhere. It is true. I mean, it has to do with this. I mean, this part is somehow motivated by symplectic structure on the double trumpet, like the cylinder, the double trumpet, and the double trumpet plays the role of a symplectic groupoid. And then for a symplectic groupoid, one kind of knows how to write the two form. So that's sort of where it came from. It took forever. So I'm saying it plays the role of a symplectic groupoid.
Right.
And so in general, when you have a Lie group, then the cotangent bundle becomes a symplectic groupoid, and there's a well-known formula for it. And there's sort of like affine analog of that. Yeah, so if you have a central extension of the Lie algebra, and then can look at this level one set, there's a symplectic groupoid for that, and there's a formula for that. So for Piazzolo, we basically know what the symplectic groupoid is, and the space for the double trumpet is that symplectic groupoid pretty much. So that's why we kind of knew the formula. Right, coordinate-free description. So yeah, it's a tricky. So actually, I want to go back to the case. Let's talk a bit about the case where the boundary is empty. No boundary. Then I explained that from every hyperbolic structure, you get a flat principal bundle, you remember. So P theta, where this P is a principal bundle over the surface, and theta is a flat connection. But knowing the principal bundle and the flat connection is not enough to reconstruct a hyperbolic metric. One actually needs a bit more. So for that, it's maybe good to give another description of the principal bundle. Again, my hyperbolic structure is defined in terms of hyperbolic charts. And I can say what the fibers are of the principal bundle also like this. So the fiber of the principal bundle at some point x in the surface is given by germs of hyperbolic charts. It's another way of saying it. So the hyperbolic chart, if I look at the hyperbolic chart, is basically unique up to the action of G, like where in the Poincare disk you send it to, and G acts transitively on the Poincare disk. So changing this germ, so this germ is unique up to the action of G, and so that's the principal action. That's why it's a principal G bundle. It has a flat connection because once you fix such a, if you have a germ, it's realized by some hyperbolic chart, and then it then specifies the germs nearby, if you know what I mean. So we kind of know how to parallel transport. That's why there's a flat connection. But then on top of all that, there's also what's called a developing map. Developing section. A map from P to D. And what this is simply, okay, so if I have an element of P, which is such a germ of a chart, I can evaluate at X. So that's another thing one has. So the full picture is actually these triples. The developing section one should take into account. Yeah, draw this up here. So this developing section is some G equivalent. So I call it developing section because it's G equivalent. So because G equivalent can be viewed as a section of the associated bundle with fiber D. But one way to think of the role of this developing section is to say, okay, G acts transitively here, and so this is G mod K, where K is isomorphic to some just SO2 rotations, and the developing section defines the reduction of the structure group. Of course, this would depend on the choice of a base point here, if to write it as G mod K. But once you choose a base point, then this developing section gives you a reduction of the structure group. That's somehow what the role of this is. Right, and this developing section, the connection, they're not quite independent. This is, so to speak, transverse to theta, in the sense that if you look at kernel of theta, which inside the tangent space, right? The kind of horizontal distribution, which is also the same thing as the pullback of the tangent bundle. So by a horizontal lift, you look at the horizontal distribution and compose it with a tangent map to the sigma. Then it's a map from something rank 2 to something of rank 2, and this should be an orientation preserving isomorphism, I mean fiber-wise. So another way of saying this is so you have the kind of horizontal foliation. So this is the horizontal theta horizontal foliation. And then you have the kernel of the differential of the sigma, and this should be transverse to it. So this is kernel of T sigma. This is transversality. And yeah, why is this important? So I'm claiming that if you have such a triple principal bundle, flat connection, and developing map, developing section, satisfying this transversality condition, then you get a hyperbolic structure. And the way it works is quite simple. I mean, what this means is that, okay, you have this map sigma, which goes from P to D, and you have a flat connection, the horizontal leaves. If you restrict this map sigma to any horizontal leaf, it's a local diffeomorphism. That's exactly what the transversality gives you. So because it's a local diffeomorphism on the horizontal leaves, you can take the hyperbolic structure and then pull it back to the horizontal leaves. So you get a hyperbolic structure on the horizontal foliation. And then the whole thing is G invariant, so it descends. Right, so that's another way of looking at hyperbolic structures. You can say are really identified with such triples up to isomorphisms of such triples. Okay, so this then smells quite a bit like good starting point for RTR bot, right? So we want flat connections up to gauge transformations, something like that. The same picture also goes through if there's a boundary. So if you don't have a boundary, then it's the same thing. Just do it like this. The developing section then takes values in d bar, and it's the same kind of transversality property. I mean, it's just a rank 2, so it's all perfectly good, even if there's a boundary. Now, one difference is that if you look at d bar, that's no longer G mod K. And it's a somewhat funny situation. So, okay, over the interior, you get a reduction of the structure group to K, to this compact group K. Let's say if I say K, I'm basically thinking of Iwasawa decomposition, like the rotations and then the diagonal matrix with positive entries and then the upper triangle. Mm-hmm. So over the interior, we get a reduction of the structure group to K. Over the boundary, so let's say again, D is G mod K. The boundary is G mod B, G mod AN. So over the boundary, it gets a reduction of structure group to that. So it's very strange that these two reductions of the structure group kind of coexist. But that's what the role is of this developing section. Right. No, but the symplectic structure. Okay, so to define omega, we have to kind of fix the principal bundle. We want kind of have flat connections up to gauge transformations, but on some fixed principal bundles. In the story that before, we always, for each hyperbolic structure, we get a different principal bundle, right? So we want to work with one fixed one and then flat connections on that one. So we have to fix P and consider flat connections on that. Now, if the boundary is empty, we need to take the P of the correct topological type. As a, we also need to take, as I explained, it's a principal G bundle. They're classified by the integers, and I need to take that integer to be the Euler characteristic of the surface. And once I do that, then okay, there is this fact that the Teichmueller space is going to be flat connections on this P. Let's use this notation for flat connections up to gauge transformations. Okay, it's a fact, but it's actually not so obvious that this is true. Because again, the flat connection does not directly give rise to a hyperbolic metric. Oh, and by the way, so if one knows this, then this defines the symplectic structure, because this is the Atiyah-Bott theory that the curvature, so the space of all connections on P has a symplectic structure, and then the group action of gauge transformations is a Hamiltonian action with mode map the curvature. So a flat connection is mode map level 0, and then you take the quotient, right? So it's like a symplectic quotient by gauge transformations. So once you know that, it's all good. But how does one know this? So with this developing section, you get another perspective. You can say, okay, if you fix E and also fix the developing section, so long as the boundary is empty, it doesn't matter which one I choose. It's just a reduction of the structure group basically to K. Then I can also say it's okay, it's a bit of a mouthful. So it's flat connections on P, which are what I call sigma positive. So by sigma positive, I mean that this transversality condition holds. I'm fixing the P, I fix the sigma, and then I look at connections which are transverse to it. And then what we divide out by is the automorphisms of P which preserve this developing sections. So it's a kind of different quotient. Sorry, it was maybe going a bit fast. So if I look at the space of hyperbolic structures, we look at these sigma positive flat connections up to gauge transformations. If I go to Teichmueller space, we also divided diffeomorphisms on the base. So that means we divided by automorphisms, and I should take an identity component here. Right. So yeah. So the fact is that these are the same. So one can see that you can also view the same space as just sigma positive connections, flat, and then you divide out by this group. It ends up being the same.
Not flat.
Oh yeah. Yeah, the sigma positive condition is just like some transversality condition. So loosely speaking, it's like an open subset. It still has its symplectic structure.
Some way to think of this as some kind of Riemannian subversion.
Yeah, I don't know.
Do you have some natural metric on the equilibrium space that is kind of?
Oh, I mean, that's a whole another box of questions. So yeah, that we haven't looked at yet. Okay, so basically what I'm getting at is this is kind of the classical picture of Atiyah-Bott, which we try to make work for the case with boundary. But then when you look at flat connections, you somehow have to specify what to do at the boundary, and we just couldn't figure it out until we came up with the idea of taking into account the developing section and rather doing this version. And you can also see that developing section will be somewhat important because of this topological type business. I mean, if I have a surface without boundary, then the principal bundles have these topological types classified by the integers. But if it's a surface with boundary, we know all the principal G bundles are just trivial. So that sounds kind of bad already. But it becomes not trivial if I take the developing section into account. So now we look at the case with boundary. Right. Case that the boundary is not empty. Then okay, so developing section on the boundary. So that's denoted del sigma, right? So this is the map which goes from P on the boundary to the boundary of the Poincare disk. Yeah, the boundary of Poincare disk, which is G mod AN. So as I said, it gives a reduction of the structure group to this group AN. The point is that this group AN is contractible. Right. I mean, the N is, I mean, if you think of, ignore the P, if you think of SL2R, then the N would be upper triangular ones in the diagonal. So that's contractible, it's just R. And the A is positive diagonal entries of determinant 1. So it's just e to the lambda, e to the minus lambda. That's also contractible. So this is just a contractible group. And having a reduction of structure group to something contractible is almost as good as having a trivialization. It gives some homotopy class of trivialization. And once you have that, then you have some integer again in the picture, right? So that then we, because if you have some trivialization of the boundary, I can sort of cap off the boundary and just glue with the trivial bundle. So there's some integers. So these things, so bundles together with developing section up to some isomorphism, they're again classified by integers. And now we pick P sigma such that, again, this E of P sigma, it turns out we have to, again, pick it to be equal to the Euler characteristic of the surface with boundary. So we have to make that choice. Right, and then we have a similar description of our infinite dimensional Teichmueller space. So, no, so it's like a global integer. So we've capped off all the boundary components. And so over each boundary component, it's over each boundary component, so to speak, trivial. And that's why there's an integer. And so it's the Euler characteristic, which is this 2 minus 2g minus r. That integer we need. And the Teichmueller space, similar to what we had before, we take the flat connections. So we pick this P sigma, so we take flat connections, which are sigma positive, which satisfy this transversality condition. And then it's up to, what is it? Automorphisms of P, identity component of that, which preserves sigma and also, okay, that's right. So yeah, it gets kind of complicated, right? So automorphisms, which such that the base map is trivial along the boundary, and the thing should also preserve sigma. Right, so we have this description, and one feels like one is done, but then one is not. I mean, one feels like one is done because this looks like a symplectic quotient, but it's actually, unfortunately, not. Again, this took us forever to understand why. So not a symplectic quotient. Well, yeah, we don't have time to go into any details anymore, but the reason is So what this notation means is that the base map of the automorphism fixes the boundary. But over the boundary, you could still have a gauge transformation. Right? Just the base map fixes the boundary, but there could still be a gauge transformation of the boundary. That gives rise to boundary terms. And that causes a problem. So how we get around this problem is, okay, it's going to do it sort of hand waving. So instead we use two steps. We introduce a space which we call Teichmueller hat, which is, okay, if you look in this notation, it's the same thing, but we divide out by automorphisms, which really are trivial also on the fiber over the boundary. So the empress of sigma. So on this space, then we still have the action of gauge transformations of the boundary, preserving the restriction of that still acts. Okay, so and then we can show, because here it's really trivial on the boundary, this really is a symplectic quotient. So on this space we still have a symplectic structure. So this is a symplectic quotient. So almost there. So we have this space which has a symplectic structure, but it's too big. The space that we want is just a quotient by this group, and the symplectic structure doesn't descend under the group action. What saves us is kind of I mean, in some sense, it's a miracle, but of course it's not. That of course, this action ends up being Hamiltonian on that space, and it has a moment map. And the miracle is that momentum map for this gauge action. Okay, one has to kind of think about where it actually takes values in and so on, but it turns out it takes values in, I mean, what is to do with Lie algebra, one has to think, but it takes values and it's just single coordinate orbit. Oh. And once one knows that, then this explains from symplectic geometry, one knows what to do. Just take the product with that coordinate orbit with opposite symplectic structure, and then divide out by the diagonal action. And then finally, one is done. So yeah, I mean, it's not a wonderful construction of the symplectic structure, but at least it works, it seems. And we can check that indeed then the residual action of Virasoro has the moment map that we had introduced before and so on. So it does the right thing. Would be nice to have a simpler construction, but that's what we have at the moment. Well, probably that's all for now, right?
Great question. So in the last part of the problem, where did you actually use that you were working on the Riemann surface with a paper ball and not with some other like Cartan geometry?
I mean, for this construction of, I mean, what I explained, this business with the principal bundle and flat connection and developing map that goes through for these general GX structures, say they're called. Maybe that's the same as Cartan geometry. I'm not sure. Right, it's just these so-called geometric structures. Goldman has written a book about them. And of course, yeah, we do expect, and this is what my student Amadreza is working on. We do expect that a similar story goes through for these so-called RP2 structures, convex projective structures on surfaces. So instead of hyperbolic structures on a surface, where the model space is the concave disk, one looks at RP2 structures where the model space is RP2. And for the case without boundary, there's beautiful results of Goldman, which says that the space of convex RP2 structures, so-called convex RP2 structures on a surface is like a Teichmueller space. And it's like the best studied example of like higher Teichmueller space. So we kind of expect that this story goes with boundary goes through for those structures. But beyond that, I don't know examples.
If I remember correctly, Ovios and you had this paper some years ago on realizing the Teichmueller space as a symplectic ocean, right?
Mm-hmm.
Where they had to introduce some other type of moment map to
Mhm.
do this. Have you tried? Yeah, that's probably without boundary. It's not.
Yeah, without boundary. Mm-hmm.
We tried. Whether their methods can be used to realize the.
Yeah, I don't understand their methods too well, to be honest. I mean, in some sense, I also found it's a bit of a, how to say, case of flat connections. So in that sense, you know already that it can be realized as a symplectic quotient.
But still, maybe
Mm.
their methods can
Mm.
still use.
Yeah, so maybe they do a bit more of the Riemannian aspects. I mean, of course, you could then ask for our context. Can you also get some Riemannian structure and Kähler structure and all that? So it's outside my expertise.
What happens with the boundary? Then the formulas simplify to something.
Well, no, in the case of a disk, we know that the action is transitive. So we kind of know in advance that we get a coordinate orbit. And then, I mean, one of course has the formula for the symplectic structure on the coordinate orbit. Yeah, the formulas are presented here. Okay, I mean, in principle, this should apply to the disk. We were just thinking about the case where you have these trumpet ends. I mean, we know separately what the symplectic structure is on the cylinder and on the disk anyway, because it's a coordinate orbit for the Virasoro group.
Various realizations of those orbits. For instance, when you glue two disks together, you have a sphere, and this. That's one of possible realizations of the Virasoro, that you have all diffeomorphisms modular notation. By using.
Yeah, but Anton, I mean, Anton has one student thinking about such things, and Anton and I also want to think about it more as one direction where we can try to generalize is to allow hyperbolic metrics with singularities. That seems to be quite interesting. I mean, so even in the case without boundary, as I mentioned, that there are all these connected components where one corresponding to Euler characteristic is the Teichmueller component. But then, except for the zero component, the other components are smooth as well. And to some extent, it seems that they can be realized by hyperbolic metrics with singularities. So that's one more direction. So Anton's student, I think, is working on the case of a disk, but introducing singularity in the metric, and then I believe the result is you get other coadjuvant orbits.
So there's no boundaries that we could identify with this connected component of moduli space of flat connections. And correct me if I'm wrong, but when we add boundaries to a surface, this moduli space of flat connections becomes Poisson. The symplectic leaves are given by fixed monodromy around the boundary. But why doesn't, so like conceptually, why don't we get something like that here? Why isn't this?
Oh, we can also, I mean, we can look at a different space. I mean, we kind of wanted to have some Hamiltonian space because we wanted to have an example, but you can look at a different space where instead of looking at these infinity boundaries, you look at hyperbolic metrics with geodesic boundary, and those spaces have been very much studied. Yeah, so it would then be Poisson, and so from our perspective, yeah, if you fix the lengths of those geodesic, they would be symplectic quotient of our infinite dimensional space. And if you don't fix the length, then there would be some sort of symplectic cross sections of our infinite dimensional space. Yeah, what the story is with connected components, I'm actually not so sure in the case with boundary. I mean, there should be some story as well, but I'm not sure if that's totally clear from Goldman's. I mean, this business with connected components was mostly studied by Goldman in terms of yeah, in terms of Pan's decomposition. So he does consider to some extent surfaces with boundary, but I'm not sure if he makes a statement of the sort that somehow the one with geodesic boundary is a connected component of something.
So, what was the use of that moment map you defined on the Teichmueller space? So, can we take a quotient for?
Yeah, we can. I mean, as I was saying, it's for us, we want to have some example of a Hamiltonian Virasoro space. So the moment map is then part of the package. So this other part of the story is of our story is that we can translate these infinite dimensional spaces into finite dimensional spaces.
What's the procedure?
Not quite so easy to explain. I mean, there's a similar thing for Hamiltonian loop group spaces where it's easier to explain. So when you have a Hamiltonian loop group space, then to each boundary component, there's an action of the loop group, and you take the quotient by the base loop group. So loops which are based at the identity, then one still has a, so then this infinite dimensional space, it turns out, becomes finite dimensional, and then one has a G action, and one can construct a two form on that space. So there's something similar for the Virasoro spaces, but it's not as straightforward that you take the quotient by something. It's more like a correspondence diagram.
If we are equivalents,
Yeah, some Rita business, yeah.
other questions?
Thank you, Eckhard.